In this video, we're going to look at some more examples of factoring trinomials in standard form where a equals 1. But we're going to look at special cases that when factoring you might be able to recognize and be able to factor a little quicker. So those two special cases are difference of two squares and perfect square trinomials. Understanding the name of them probably isn't as important as just knowing how to factor. So we, as always, want to see if there's a common monomial we can take out to simplify. But the main thing is we're looking at the c value and checking if it's a perfect square. So the two examples I have here, I have 16 as our c value, and that's a perfect square. Square root of 16 is 4. So you see we've got 4s in our factors here. So in this first example, if b and c are positive, assuming it is factorable, you have a perfect square trinomial. So what that means is you have a trinomial here. You've got your three terms, so trinomial with a perfect square as your c value. You'll notice that since these are both positive, then in this video we're going to look at some more examples of factoring trinomials in standard form where a is still equal to 0, but there are some special cases that if we recognize, it can make factoring go a little quicker. So the special cases are difference of two squares and perfect square trinomials. The names of those isn't as important as understanding what to look for when factoring. So we still want to look for a common monomial to take out and simplify our expression or equation, as always. But the main thing here is our c value is going to be a perfect square. So our first example here, we have x plus 4 times x plus 4. So we notice we have the same binomial being multiplied by each other. So we could write this as x plus 4 quantity squared. When we multiply that out, we get a 4x and another 4x if we think about our foil or box, and we get 8x. And then 4 times 4 is going to give us our c value of 16. So that's where our perfect square comes from. And this one is a trinomial, and we have a perfect square there for a c. So that's kind of where the name perfect square trinomial comes from. That's when this is factorable. And you'll notice that the square root of our c value, when you double that, that gives us our b value. If we look at the second example, it's still the same numbers, but opposite signs. So x plus 4 times x minus 4, well, a 4x and a negative 4x are going to cancel each other out. So that's where we get a b value of 0. Well, we're not going to see plus 0x in our polynomial. So since it doesn't look like a trinomial, it doesn't look like typical standard form, so we don't always recognize when we see this how easy it can be to factor. When you have a difference of two squares like this, you're always going to get a negative c value. Up here, if this happened to be x minus 4 and x minus 4, we're still going to get a positive 16, but the 8 would be negative. Okay, so our first example, we've got x squared plus 12x plus 36. So right away I notice that this is a trinomial, so if it's going to be one of our special cases, it's going to be a perfect square trinomial. And I look at c value, it's a perfect square. Square root of 36 is 6, and 6 plus 6 is 12, and everything's positive here, so that tells me this is likely going to be x plus 6 times x plus 6, or if we want to write it in a simplified version, we would just write x plus 6 quantity squared. Our other example, we've got x squared minus 81. Again, I see this and I don't recognize standard form right away. That's just usually how our brain works. But I notice that we have the x squared, we have the perfect square for a c value, and it is negative. And since there's no b value, this is likely a difference of two squares. Square root of 81 is 9, And so we would have x plus 9 times x minus 9. And this is an example of difference of two squares. Now you might see some variations of this. A value doesn't have to be 1. We kind of use this basic example and just expand it. So let's say we actually had, let's go 4x squared. Well, the 81 is still the same. We still have a positive and negative 9 here. There's no b value still because that 9x is going to cancel with the negative 9x. So now we're trying to think of, well, x times x gave us x squared. So what could these two values be? They're the same. So when we multiply them essentially by each other, we get a 4x squared. Well, 4 is also a perfect square, just like 81 is. And square root of 4 is 2. So if we think about this example here, 2x times 2x is 4x squared. 2x times negative 9 would be negative 18x. And 9 times 2x would be a positive 18x. So we still end up with a middle term canceling out, so no b value, and then we still have our negative 81. So this really only works if the a value and c value are both perfect squares. If this was a 3x squared, well, then we're getting into square roots where we don't have integers that work out that multiply to 3 because 3 is not a perfect square. So I'll change this back to a 4. I'll leave that. Well, when you get into upper level math, you might see some examples where you have multiple variables in your equation or expression. Make this a little wider here. Okay. So now in this case, the 4x squared is still the same, so we still want to keep the 2x and 2x. We still have the negative 81, so the 9 and negative 9 stay put. But now we have a y squared. Well, we just think about how this is an x squared, so the first term in each binomial, in each of our factors, is an x, because x times x gives us x squared. Apply that same concept here, y times y would give us y squared, and we did 9 times 9 to get 81. Well, now this is in the same term, so if we do 9y times negative 9y, that's going to give us negative 81y squared. So just some variations there with that difference of two squares example.